video. So as far as the grading goes, the purpose of the homework is to help you understand the concept. That's why I give you 3 attempts. My thought process there is that if you go through it once and you think you figured it out and you understand it, then you can go through it twice. If you're still hitting a wall, or if you spend a tremendous amount of time on any one topic, so in other words, the rule of thumb I give everyone, if you are more than 30 minutes into a homework problem and can't figure it out, that's time to reach out to me, the tutoring center, Discord, any of your tools. So learning shouldn't be something that you spend a gajillion hours on getting nowhere. There is a point of no benefit return when you do those things. And so that's the philosophy on the homework. In reality, most of you should get 100% on the homework. So it's not something that you should lose points on. It's something that you should learn from. So if you see something that is wonky as far as the grading goes, let me know, because until somebody speaks up, I assume that it's grading as I think it is, not some random value assigned to something, because it definitely shouldn't be. It should be consistent. Does that make sense to everybody? Cool. Let's see if I can see that. All right. So I'm going to start off. To those of you that were here, this is the handout for projectile motion. So I get a little bit nervous when I don't see discussions on Canvas, or not on Canvas, on Discord, and I'm not getting office hour requests. And to back up real quick, the decision I've made, because my office hours have been going fantastic by request, is to send me an email for any times that you need to meet. So if you need to meet on a Wednesday or a Monday at regular lecture times, and that's best for you to get help, then by all means, I'm totally fine with that. That's what I've been doing, and it's been working beautifully, getting a lot more folks helped out than setting set hours. So send me a request. I've been able to accommodate 99% of the requests for times, so I can work with you. Now on the handout that we're doing today, I'm back to what my point was. Because I've not gotten questions, I wanted to start with a projectile motion problem. Don't look at my notes. Don't look at the video. I'm going to send you into groups, into breakout rooms. I want you to tackle problem number 2. And then we're going to come back and have some of you explain how you got to your answers. So with this one, I'm going to give you 10 minutes. So 10:13, we'll come back into the main room. If you can't find the handout or just don't feel like looking, go ahead and take a screenshot of the question. If you're unfamiliar with how to do that, hit Control and print screen, and then you can just paste that into a Word doc or whatever, and bada bing, bada boom, you have the problem. All right, so stop sharing and start breakout rooms. Oops, there we go. All right. There you go. I will see you in 10 minutes. Come back if you finish before then. All right. So which group would like to volunteer how you approach this problem? Jack, go ahead.
All right. So first we sketched a diagram of us, our height, the height of the apple, the distance from it, and the angle at which we were shooting. We then used SOHCAHTOA to find the actual perpendicular velocity of our projectile and the horizontal velocity. We then took our perpendicular velocity to find how many seconds it would take to reach the apple. And we used that. So we used the time, our initial velocity, our acceleration of negative 9.8 meters per second, and we used that to find the where or how high the object would go using the equation y0 plus v0t plus 1/2 ayt squared.
Sweet. Now, did it hit?
Nope.
Oh, no. So where would I need to stand if it didn't hit or to make it hit?
We would have needed 5 more minutes for that.
Okay. Okay. So let me just kind of sketch out exactly what you said so I can share it with the class. Actually, let me share my screen while I'm doing it. Just in case everybody didn't get that. All right. So you did the drawing I have here. Let's see, here's my 34 meters per second. And this distance here is 45 meters. Let's see. My arm height, so this is 1.4 meters above the ground, and the apple height is 4.9 meters above the ground. That's pretty much what you sketched out? Perfect. Okay. And then you said you went with what?
We used SOHCAHTOA to find the horizontal and vertical velocity of our projectile.
Okay, so let's see, V not in the, let's actually, let me make this little meter. So we'll go Y and X. And Y, what trig function am I using there?
For our Y, we used sine of 32 equals opposite over hypotenuse, so x over 34.
Sweet. And then the opposite would be true for here. Any questions on how that part came together? Is everybody comfortable with that? Okay, I do want to emphasize this in case somebody's just feeling shy about asking. Is that, remember, here's my 34 meters per second. To find my components, I'm looking at this 34 and I'm looking at that and I'm saying, okay, so I'm going to have a vector piece going like this in the X. And then I'm going to have a piece perpendicular to that in the Y. If I know this angle, I'm just going to call it theta for space. And I know the hypotenuse, the rest is Pythagorean. It's just a squared plus b squared equals c squared. Right? But in this case, I don't know my a squared or b squared. So getting to my x and my y with that isn't going to be helpful. So I do need to use my trig. And then we have, let's see, cosine equals adjacent over hypotenuse. And sine equals opposite over hypotenuse. And one of the most frequent questions I get is, especially for the adjacent side, how do I know that I have the right adjacent side? I mean, the 34 meters per second side is also touching the angle. So how do I know that's not it? So what you're looking for is the two pieces that are perpendicular to each other. We're creating that right triangle. And so if my 34 isn't perpendicular to the X or the Y, then that is definitely my hypotenuse. And it, to some of you that might feel like, well, why is that a problem? Sometimes it's not as visually obvious, right? And so that is my resultant. This here is my resultant, or my C side. Sweet. So if I want my horizontal component, which would be the V and the X is touching the angle, so it is my adjacent side. The V and the Y, well, if I look at it, it's looking opposite of the angle itself. Just pretend like it's an eyeball. So that's going to be the opposite side. So I'd use my sine function. So now I have that. Let's see, let's just go ahead and make a list of the things we have. So this is my initial Y velocity. Do I know what my final Y velocity would be, say at this point here? Just by looking at this? Nope. We'd have to actually figure that one out. So I don't know that. But do I know my acceleration?
Yes.
Yep. 1.8 meters per second squared. And as I'm doing this, let's go ahead and define. So one of the things I want you to get in the habit of, and with the exam coming up, this is a critical piece, is define for me what you're saying is positive, because I cannot make any assumptions. And if you have any mishaps with signs in your work, I have no idea where that's coming from. So you must always define for me what's positive. So if I define up and to the right as positive, that means my gravity, my acceleration vector, which is always pointing down towards the center of the earth, is going to be negative. Cool. So we have that. Let's see. Do I have a delta y? Well, it kind of depends. If I want to approach this problem as though I'm actually going to make it to that height, then I could just take the difference between the 4.9 and the 1.4. But if I'm not sure, then I'm just going to put a question mark there. And I don't know time either. So I know my V naught in the X and the Y. Do I know my V final in the X?
Yes,
Yes, what would it be?
it's 28 point something meters per second.
I'm sorry, you said it's what?
28.83 meters per second.
0.8 meters per second. And let me ask you, how did you get that?
From I found the x component of the vector using I don't know, SOHCAHTOA. I don't.
Nope, nope. So in other words, my V initial is my V final in the X?
Yes,
Sweet. Why?
because we are ignoring air resistance.
Perfect. So what does that mean as far as acceleration?
There's no acceleration.
Beautiful. Perfect. Do I know the distance I'm going to go?
Yes,
Okay, what's that distance?
45 meters.
Beautiful. And do I know the time?
Yes.
I do?
Well, we can find it with those two things that we just got.
Perfect. And the reason why I'm asking that is because it is handy to remind yourself that if I have no X component, then the only math I can do with the, I'm sorry, if I have no air resistance or anything, any force acting in the X direction, then the only math I can do here is rate times time equals distance. And I can put that in terms of velocity. And if you look at this and I rewrite it, well, what is this? Well, this is just saying that the change in position with respect to time is my velocity with no acceleration. That's what I want you to highlight. This definition of velocity works perfectly for actual motion if there is no acceleration. If I use it when there is acceleration, the answer I'm actually getting back isn't an instantaneous velocity, but an average velocity. Does that distinction make sense to everybody? It's probably the most common mistake I see made. And it is the one thing I want to emphasize, because when you get stuck and you can't figure out where to go, if you remind yourself that if I have two of those three pieces, I can solve for the third piece like straight away. So in this case, if I wanted time, I can go, so then my delta X divided by the V initial will give me my time, which is what I think Jack said he did. Is that correct? Sweet. So what did you get for time?
Could you solve out the V initial if that's okay?
Solve out, so for the X component?
Yeah.
So my V initial in the X then is going to be that 34 meters per second. That is the hypotenuse times cosine of,
Okay, so it's just that formula.
yep.
Okay.
And this is from the trig function. So that comes from, I said that, let's see, cosine of an angle equals the adjacent over hypotenuse. Where here the hypotenuse is my resultant velocity, is the actual speed at which this rock is leaving my hand. So I can rewrite this then as let's see, my actual velocity, my total velocity, not a component of it, times cosine of whatever angle that is. So this is my hypotenuse, will give me the x component. Now, let me ask you this, because this is another common mistake that I see. Is the x component always going to be cosine?
No.
Nope. Because I can draw the same picture and have the adjacent side be the y component. So take heed with that. You will get the exact same answer, whether you do sine or cosine, because the angle itself is going to change. So you'll get the correct value. It doesn't matter which angle you actually use, so long as you're picking out the piece that is actually the y vector or the x vector. Does that make sense to everybody? And you're going to see this as we move on next week in particular with our forces, because we're going to be doing things all over the place. Are we all good with that? Did that answer your question? We're good? Okay. So I'm sorry, what did we get for time?
1.56 seconds.
Sweet. Okay, so we got that. And the nice thing is what I want to know, the bridge between these two pieces is time. So even though they're components, at some specific spot, they're going to have the same amount of time getting there. So this time that I'm looking at here is what's happening in the y at 1.56, because that's how long it takes to travel that x direction. So that's where the rock is. We want to know where the rock is going to be relative to the apple. Is it going to be at that height, or is it going to be above or below it? So now, as Jack was saying, I think you took the time and then you plugged that into which?
The time with the major equation, we put that into y equals y0 plus v0t plus 1/2 ayt squared. Not sure if I'm saying that right.
At squared. Yeah. Yeah. And the subscripts are handy. Not necessary when you've written it out that you're defining this strictly in terms of y. But if you're having a hard time keeping track of what subscript goes to what, then that's what you'd want to do. So now I need to remind myself my initial velocity in the y is going up, and I've defined that as positive. But my acceleration is pointing down, and I've defined that as negative. So I'm going to go ahead and just make this negative. Or there's nothing wrong with, if you've made this notation here that your acceleration is negative, to leave it as a plus and then plug in your negative value. Whatever you need to do to keep it straight, so you're not double inserting a negative value that shouldn't be there. Does that make sense? You inadvertently have acceleration due to gravity speeding something up when it's actually slowing it down. And that's just the quick check that you can do with yourself as you're doing the math, is being like, so should this thing be slowing down or should it be speeding up? All right, so then we can put in our values. We don't know what delta y is. That's what we're going to solve for. Equals our v naught t. So we have our 34 meters per second cosine of 32 minus 1/2 times 9.8 meters per second squared times t squared, which is our 1.56. Cool. And so what do we get for that? What was the change in height?
Don't we also want to multiply by time in the first, like 34
thank you.
cosine 32?
Thank you. Yep.
Okay, cool.
Yep. Times time. 0.56. And that mistake can be easily found if you do a quick units check after you're done. Because if you're getting an answer that nobody else is getting, sometimes that's just what happens. You get going fast and you drop something. Okay. So what do we get for our change in height?
16.2 meters.
Cool. So what does that mean as far as our
We
picture
are
goes?
much too high.
Yeah, so that means at the time I hit here, my rock is way the heck above the apple itself. So then the next question I ask is, where would I need to stand? So I want to maintain that initial velocity, but I want to actually hit this apple.
So we have to solve the equation we just had, the delta y equation.
Okay,
We have to throw out what we think the t value is and solve for a new t.
beautiful.
Quadratic equation.
Cool, cool. So then the delta y I'm looking for here, let's see, let's just write it here to hit. I need my delta y then to be that 4.9 minus my 1.4. Because that gives it the height that it needs to be. And remember, I'm starting at the 1.4 and the 4.9 is the total distance from the ground. So I just need that change in distance to make sure that my projectile is at that height. So let's see, what do I get? I get 0.5, 3.5. That's my delta y. Is everybody good with that? Cool. All right, so I know my delta y. I know my initial velocity. So I agree. This one will do. So I can go then, let's rearrange the, oh no, yeah, I'll rearrange it. I'll show you my steps. Delta y, v naught t. Yeah, go ahead and do this. 1/2. I'm just reminding you, I'm putting in the negative gt squared, because I've already accounted for the direction of that vector. So then I'm going to do a quadratic. And my preference is to not have negatives where I have my squared term. So I'm going to move everything over to the other side. So I'll have 1/2 gt squared minus v naught t plus delta y. And that equals 0.
What's the G again?
G, remember, is the acceleration due to gravity.
Okay, okay. And you inputted that instead of acceleration?
Because in this case,
Or, oh, you just changed, I see.
Yeah,
Okay,
the
you
only
changed the G for,
the only thing accelerating it is gravity, so we can just use G. Thank you for asking that. All right, so let's see, what do we got? We got 1/2 times 9.8, otherwise known as 4.9, t squared minus, now I'm going to use the value we have instead of writing it out so I have space, 28.8 times t plus 3.5. Now here's the part I don't expect anybody to show. I know that you've been shown the quadratic equation. I know that most of you can plug and chug, but I am totally also comfortable with you either using your calculators for as a quadratic solver, or there's Purple Math, like Quadratic Solver online, I think, or Math is Fun. It's one of those websites where you can put in your values. Just make sure you include your positive and negative values there. And then at this point, once you've shown me this, you can now just give me your answers. All right, is that clear to everybody? Cool. All right, so what times do we get?
There's one very low, it was 0.205 seconds, and then 3.47 seconds.
So what are those two different times?
Those are the two roots of the quadratic equation.
Okay, but physically, somebody else. What do those two values mean?
One of them is how long it takes to hit if you're standing close to the apple and it hits on its way up. The other one is how long it takes to hit if you're standing farther away from the apple and it hits on the way down.
Perfect. Absolutely perfect. Yep. So the shorter time would be if I'm hitting it and it's on its way up, it's making its way up that trajectory. And the other one is I'm far enough back that it's gone up and it's on its way down and hitting. Perfect. So I can choose either of those. I now know the time. So now what handy dandy tool do we have to solve the last step of where I need to stand? Somebody else.
Multiply the time by in our first equation with the x
Perfect.
velocity. Multiply that by
Rate
the-
times time equals distance is your bestie. And it will simplify life if you just kind of keep that in the mind. My velocity in the x is constant for most projectile motion, unless I get outside and it gets truly windy. Then we'll see an impact. And there's a video that I've shown that shows the cart in the box, and that's in a room with a cart or ball, not a box. The cart launches the ball up in the air, the cart keeps moving at constant velocity, and the ball lands right back into the cart. So it's not just voodoo that we're doing here. It really does take more than just a stale room of air to impact the motion in the X over short distances. When you get into things like launching a rocket or whatever, now those things are going far enough that those small changes in air resistance will have an impact. Then you would want to include it. That's well above and beyond this class. Are we all good with that? So for there, I'm sorry, go ahead.
I had a question about why you use the x velocity in that equation instead of the y velocity.
Did I use the? I sure did. Thank you. That was unintentional. That was unintentional. What was the y velocity? I was being lazy and not wanting to write the 34 sine 32.
18.01.
18.01. Thank you for catching that. So then I can go that my delta x then is going to be either, now let's use the correct velocity, 28.8.
Real quick, wouldn't
Yeah.
the it would be 18.02 because it's 18.17, or how do you want us to do rounding and significant figures during this sort of math?
Okay, so here's the fun part. Sig figs are really embraced in chemistry, as they should be, and physicists get way too lazy with sig figs. My suggestion to avoid rounding errors, especially for homework, is to take it like 2 after the decimal. Makes you pretty safe. However, I mean, if I look at this, I have like 2 sig figs and everything. So my answer, I should really only be working with like 18 if I wanted to be sig fig conscious. Because your textbook, and it's the reason why I bounced back from not emphasizing sig figs, is the textbook and mastering are very inconsistent with the amount of sig figs they use. So it becomes more confusing than it is helpful. So hopefully in lab, they emphasize the importance of the sig figs for your answers, because that's really where the rubber meets the road, is that your sig figs should never be more precise than the precision of the measuring tools that you have to your exposure that you have to use. I don't know what word I was looking for there. Does that answer your question? So not to be overly vague, but I don't mark off for sig figs in physics, but you don't need to give me every digit that your calculator spits out either. So 8 decimal places is probably overkill. And not probably, it is overkill, especially when you only have 2 sig figs to start with. Does that answer your question?
Yeah.
Cool. All right, so we have 28.8 Yes, I'm using the right. And then 0.205. And then delta x, let's call that 1. Delta x2 then would be the same, my 28.8 times my 3.47. And there we have it. That will tell you how far away you need to stand to launch and hit said apple.
I have a question.
Yeah.
Is our times going to be different since we substituted the different velocity, or is that going to be the same?
I'm assuming that I'm the only one that made that mistake. So whoever did the time calculations, did you use the X? Or did you use the Y?
I just checked and the times were for the Y.
Okay, cool.
Okay.
Thank you.
Okay.
Thank you. Awesome. So there's a few things that I want to make clear here is that your problem solving approach is going to save you in dividends. If you just kind of blow through these and get in a plug and chug kind of mindset, then you're going to do yourself harm as we're moving on into forces, which is what we're going to start for just a couple of minutes before I let you all run free today. And the reason for that is we're going to be dealing with a lot of variables and very few numbers to begin with. So you need to be comfortable with that kind of manipulation. And that's what most of my office hours have been for 114, which is what had me nervous with y'all. So do me a favor, if you're not comfortable with this, reach out to me and we can work through it. And we can work through some of the more challenging problems until you get comfortable with seeing a nice pattern. The two things I always say, draw a picture, make a list of what you know. And then the one thing I didn't do here that I always do is then I scratch out somewhere near to me a list of my equations. So I'd be like, I got v final squared equals v naught squared plus 2a delta x, where delta x can be delta x or delta y. Then delta x equals v naught t plus 1/2 at squared. And then just the standard definition, I can write it to remind myself that acceleration is just my change in velocity with respect to time, the rate of change of my velocity. How much it changes is by definition what my acceleration is. And my velocity is my change in position with respect to time. And then the most important thing for all y'all to remember is that these only apply if I have either constant velocity in the definition of my velocity with displacement with respect to time. And with my accelerations, it only ever works to use these equations. Otherwise, I have to use calculus if my acceleration is constant. If my acceleration is not constant, then I cannot use these algebraic equations of motion. Is everybody clear on that?
I had a quick question.
Yes.
I know
Yes.
this is kind of a little bit different from what we have been doing, but are we ever going to be graded on like the type of work or the type of mathematical formulas that we use for this?
I'm
Or
only ever going to let you use these three formulas or four.
okay, so are we not allowed to parameterize motion vectors and use that?
Help me out with what you're trying to describe.
Looking at like I and J components and
Oh, yeah. No, so if you wanted to do that, absolutely. No, but as far as grabbing equations, so yes, if you want to use calculus, if you want to use your I and J components, the reason why I don't harp on that to begin with is so many of you are still learning it.
okay.
So I don't expect everybody to bounce along and be able to pull those tools out right out of the gate.
Okay, but we can use like derivatives of vector components. and
Absolutely,
Tools
absolutely.
like that. Okay.
What I don't want you to do is to Google what equation to use for how high will the ball be.
Yeah.
Yeah.
Okay. Thank you.
Thank you for asking. That's a great question. And with that, you know what, with only 4 minutes left, I'm going to hold off on my intro to the forces. And I understand this puts us a little bit behind, but we're still on track with the labs. I don't want to shove too much down your throat trying to keep everything on track after you lost so much of my time last week. So again, come see me. Don't hesitate. It's no big deal. And a lot of people have been hitting me up from the other class. I don't know if you think that perhaps I assume that you should know how to do things, or maybe you all totally get it, which would be awesome. But if you don't, not a big deal. Hit me up and we will work on it. Okay. We all good?
I just had one final question
Yeah, sure.
for the final answer, like how far we have to stand back. So we get like 5.9 and then 99.94 meters after we plug those in. So I see that they said that there should be two options. Are both those options correct?
Yeah.
Okay.
Yeah, because I didn't say, where do I need to stand if I want to hit it on the way up? Or where do I need
Okay.
to stand if I want to hit it on the way down?
Technically, there are 4 options, right? Although I guess that would result in a change of velocity if you went on the other side.
Yeah. Yeah.
Okay,
Yeah. So if I want to keep the sign of my velocity the same.
got it.
Yes.
Okay.
We all good? All right. I'm going to stop sharing and stop recording.